Hi, my name is Patrick Cooch, and I am the I/O Virtualization TME for the Intel LAN Access Division. And this is going to be part 2 of a discussion about the technologies in some of the Intel Ethernet controllers that assist Ethernet I/O in a virtualized environment. Part 1 discussed VMDQ, and now this part 2 we're going to discuss SRIOV. So by way of a review, let's look at how Ethernet traffic in a traditional virtualized environment works. So an Ethernet packet comes in and an interrupt is fired. You have one core that's assigned to handle all the interrupts for the NIC. That core has to stop what it's doing. So if it was processing a virtual machine, it has to stop what it's doing and go look at and go get that packet. Next, it has to look at that packet, it has to examine it, has to open it up and take a peek at it and see what its destination MAC address is or VLAN tag. And based upon that, they can determine which virtual machine that packet is supposed to go to. And then it has to go interrupt the core that is currently running that target virtual machine. So then that core comes and gets the packet and it copies it to the memory space of the target virtual machine, and then it continues processing. And then the core that was interrupted to service the packet that came in can continue with its operations until the next interrupt occurs. So as we discussed in the first presentation, the challenge with this type of situation is that you have a single core that's assigned to handle the interrupt for all incoming packets. And it easily gets overloaded when you're trying to do 10 gigabits worth of traffic. And also, every packet that comes in usually results in two cores being interrupted, one to service the interrupt on the NIC, and another one to actually manipulate the data and copy it to the virtual machine, thus having some performance degradation. So as we discussed in the first presentation, Intel VMDQ technology breaks the packets into queues based upon the destination MAC address or VLAN tag, and each queue has its own interrupt, allowing each core to have a different queue assigned to it and a different interrupt, thus spreading the workload across all the cores and improving performance dramatically. VMDQ has a great benefit in doing this. However, with every packet that's received and transmitted, the hypervisor still has to physically copy that data from the virtual machine to the NIC and from the NIC to the virtual machine. So that for every packet coming and going, the hypervisor has to actually physically touch each of the packets. So this is where SRIOV comes in. SRIOV stands for Single Root I/O Virtualization. It's based upon a specification developed by the PCI SIG. Intel was one of the major contributors to the specification. And essentially what SRIOV does from a very high level perspective is it has these what we call virtual functions. And in this slide we see three of them, pool 0, pool 1, and pool n-1. And each one of these virtual functions has dedicated queues to them for transmitting and receiving, and they have lightweight PCIe resources. That means that they have registers and bars and that kind of stuff, but just enough essentially to be able to transmit and receive data. In addition to these virtual functions, we have what we refer to as a physical function, which is your normal, what you would usually think of as your Ethernet port. It's your transmit and receive descriptors for your driver can tell the NIC where to send data to and from, and then link control and offloads, all that kind of stuff, security, etc. Everything that you associate with a regular NIC port. That's a heavy or a large full-functioned PCIe device, or PCIe function is the proper term. Whereas a virtual function is very lightweight, and it just has enough information in there to be able to transmit and receive data to and from these queues. And just as in VMDQ, a packet comes in and is sorted and put into a specific queue. So here's another view of that. And what this is showing is that in this case, each virtual machine is directly assign these actual hardware resources. They're assigned and given access to these resources by the hypervisor. So now these VMs, they load up a driver. It's a specific driver, a virtual function driver. When the VM boots up and it goes out and probes its PCI config space, the hypervisor tells it what it has. And in this case, it's going to tell it has a virtual function, and it's going to point it to the registers where this thing actually exists. The driver is going to load up, and it's going to go fill out those descriptors we saw on the previous page, telling it exactly where to copy data to and from in the memory owned by the virtual machine. So there's dedicated queues for these resources, just like we had in VMDQ, and dedicated registers for each one of these virtual functions, and they're assigned to each, can be assigned to each virtual machine. So now let's have a flow, an example flow of an actual packet coming in and being copied to the guest OS, into the VM. So a packet arrives. Then this packet is sent to our layer 2 sorter switch, and based upon the MAC address or VLAN tag, it is placed into a specific pool, and when it reaches the top of that pool, it is then going to be DMA'd using the descriptors that the driver in the virtual function driver in the VM fills out. It's going to DMA that data. Now, the locations where the driver fills out the descriptor saying where to copy that data to, where to DMA it to, is a virtual address. It's not a physical address, because the virtual machine doesn't necessarily know where it actually resides in physical memory. So the DMA actually hits the chipset, and Intel VTD, which is IO remap. So here's an animation showing SRIV in action. A packet comes in, and it's sorted into queues. There's one queue for each, or one set of queues or pools for each virtual function, and a packet comes in, placed into a pool based upon the destination MAC address or VLAN tag. Then the data is DMA'd directly to the guest OS's memory space. This is done because the virtual function driver that is loaded in each one of the VMs has direct hardware access to those transmit and receive descriptors we saw earlier. So when the NIC is ready to DMA data, it uses those descriptors. It DMAs the data directly to that location. The DMA operation hits a chipset. The chipset, using VTD technology, remaps that destination address to the correct address rather than a virtual address. It's now a physical address, and then it continues the DMA operation. So using SRIOV, you can DMA data to and from the memory of a guest OS, of a VM, directly without any software ever having to touch each packet, thus significantly reducing overhead. So by way of a summary, what SRIV does for you is that it removes the hypervisor, the VMM, completely from the process of moving the data from your NIC to your guest OS, or from the VM to the NIC. This is done because each guest OS now, each VF, has direct access to hardware resources that are dedicated for each virtual function, each virtual machine, dedicated for I/O, dedicated for transmitting and receiving those Ethernet packets. So the software switch does never get involved, does not have to touch any of the packets, so the packets are moved directly to and from using hardware. So here's a list of the Intel Ethernet controllers that have hardware capabilities that are specifically designed for virtualization. On the left side, you can see we have a number of them for virtual machine device queues, VMDQ, which I discussed in the previous video. And we have two controllers currently that support SRIOV, one 1 gigabit controller and one 10 gigabit controller. This last slide, I suggest you pause this video so you can see it all, but essentially it's a number of resources, including data sheets, which has all the ones and zeros and what everything does in the controller, white papers, source code for both VMDQ and SRIOV, and even some documents on if you want to write your own drivers. You can look at our open source drivers for SRI.